Welcome. This video is about the quietest, most relentless artist in your life. Gravity. By the time we're done, you'll have a complete, plain language picture of what it is, how it pulls on everything from your coffee mug to a black hole, and you'll be able to explain it clearly to someone else. Right now, wherever you are, whether you're sitting at home, riding in a car, lying in bed, or watching this on a break, I want you to pause for a moment and actually notice your body. Notice where you're sitting or standing. Notice the shape of your spine, the angle of your legs, the way your head balances on your neck. Now, pay attention to the feeling of weight, the pressure of the chair under you, the way your feet press into the floor or your back presses into the mattress. Maybe your phone or laptop rests in your hands, and you can feel its gentle pull downward. Think about that for a second. This constant sensation you almost never think about. That's gravity quietly at work. It's not just an idea from science class. It is a continuous physical experience, pressing on every atom in your body, every second of your life. Here's the key rule for this journey. No equations, no prior physics knowledge required. We're going to move slowly, patiently, step by step. I'll be like a friend sitting next to you, using ordinary words, simple examples, and only the pictures your imagination can draw. Because gravity is strange. It's the most familiar thing you know, and at the same time, one of the least understood. It lets you walk instead of float away. It keeps you curled up under a blanket at night. It holds the oceans to earth, choreographs the moon's dance in the sky, and shapes the paths of planets and stars. But it also does something wilder. The same gentle pull that keeps your feet on the ground can, when enough mass is squeezed into a small enough space, create a black hole where not even light can escape. So soft on your shoulders, so steady under your chair, so powerful it can bend time itself around your body. Here's something that will make you smile. You're already an expert user of gravity. You lean, jump, pour water, drop your keys, all without thinking. What you don't yet have is the story that ties all of those everyday moments to the way the universe is built. So in this video, before we can understand the wild stuff like warped time and black holes, we have to understand the simple feeling of sitting in that chair. By the end, you'll see why falling objects, orbiting moons, and even the ticking of your watch are all chapters of the same story. And once you see that, gravity finally starts to make sense. So let's push that everyday feeling to the limit. I want you to take a deep breath and imagine something that sounds impossible. Imagine that, just for 1 second, gravity turns off. Not just in space, not just somewhere far away, but everywhere in the universe, including right where you are. Pause for a moment. Look around the room you're in. The chair under you, the floor, the walls, the ceiling. In our normal life, gravity is so steady, so reliable that it feels like part of the background. But in this little thought experiment, we're going to yank it away like someone cutting a hidden string. Here's the key rule for this scene. Everything keeps whatever motion it already has. No pull, no weight, nothing holding anything down. Think about that for a second. Your body is pressed into the chair right now because the chair is pushing up on you, resisting gravity's pull on your mass. The instant gravity vanishes, that pressure disappears. You and the chair are no longer stuck together. You don't shoot through the roof like a rocket, but you do something stranger. You just drift. The tiniest wiggle you were making, the slight motion from your breathing, even the spin of the earth under your feet, all of that suddenly matters. Your body lifts from the chair in slow, ghostly motion. Pens, phones, keys all rise with you, as if the whole room decided to become an astronaut training lab. Now imagine your drink. Water doesn't politely stay in cups because it likes good manners. Gravity is constantly pulling every drop down. Turn gravity off, and the water leaps out, forming shimmering blobs that hang in the air. Here's something that will make you smile. The same thing happens to your bathtub, your fish tank, the soup on the stove, and every ocean on Earth. For that 1 second, the seas bulge upward, trying to escape the planet. Cars lift off roads. Trains leave their tracks. Buildings don't exactly explode, but they lose their weight. Bolts and beams that were designed to push back against gravity suddenly have nothing to push against. The whole world goes into slow motion chaos. Now zoom out with me. The Earth is not sitting still. It's constantly falling around the sun because of gravity. Turn that pull off, even briefly, and Earth stops curving in its path. It flies straight, like a stone released from a sling. The moon does the same around Earth, shooting off on its own lonely line through space. And here's the wild part. That single second never gets undone. Even when gravity snaps back on, the Earth and Moon are now in the wrong places, heading in new directions. Their orbits are permanently changed. The quiet, graceful dance of planets and moons has been knocked off rhythm by a 1-second glitch. Before we can understand why that tiny pause would rewrite the entire solar system's future, we have to understand what gravity is actually doing to motion in the first place. In the next part, we're going to rebuild that picture from the ground up. And when we do, the idea of falling will start to feel completely different. So let's slow down and look at what you and I usually mean when we say gravity. Most people carry around a kind of cartoon version in their heads. Gravity is the thing that pulls stuff down. You drop your phone, it falls. You jump, you come back. End of story. I want you to imagine what that looks like in your mind. Probably an arrow pointing straight down, right? Ground at the bottom, sky at the top, and gravity is like an invisible hand yanking everything toward your feet. It feels like it only really shows up when something is falling, or when something is big enough, like a planet, to have real gravity. Here's the key rule in that everyday picture. Big, heavy things pull. Small, light things just get pulled. A planet has gravity. A pebble? Not so much. And somewhere in there, gravity starts to sound like a kind of invisible magnet for heavy objects. Magnets pull metal. Gravity pulls mass. Simple. Think about that for a second. That picture isn't totally wrong. It works beautifully for catching a glass before it hits the floor, or for understanding why a ball thrown up comes back down. But it's also quietly misleading, especially once we leave the comfort of down. What does down even mean when you're out between the Earth and the Moon? Or when you're near a black hole where every direction seems to be inward at once? Let me give you the clearest possible example. Right now, wherever you are, gravity is not just acting between you and the Earth. Your body is pulling on your chair. Your chair is pulling on you. Your phone is pulling on your hand. And, tiny but real, you are pulling on distant stars. And they are pulling on you. Gravity is not a special feature that only planets unlock at level 10. It's a relationship between every pair of objects with mass. Everywhere, all the time. Here's something that will make you smile. Technically, you and I are gravitationally attracting each other through the screen. The pull is absurdly small, but it's there. Suddenly down doesn't sound like the full story anymore, does it? So I want you to notice the pattern interrupt here. Instead of thinking gravity pulls things down, start trying on a different idea. Gravity organizes paths. Not just falling paths, but the paths of planets, moons, light, even time itself near a black hole. By the end of this video, downward pull is going to feel more like a shadow of something deeper. To get there without losing you, we're going to do this in 2 steps. First, we'll build a really strong, intuitive Newton-style picture, where gravity is a pull between masses that explains orbits and falling in a way you can feel. Then, once that's solid, we'll gently flip it into Einstein's picture, where that pull turns into curved space-time and everything is simply following the shape of the universe. So here's our deal. This is not a 5-minute fun facts about gravity reel. This is a long, deep dive. And that's on purpose. Gravity is quietly doing everything, everywhere, all the time. And to really understand it, we have to slow down and walk through it together. I want you to think about that for a second. The same thing that makes your keys hit the floor is also steering planets, stretching time near a black hole, and sending tiny ripples through the universe that we can literally hear as gravitational waves. That's a lot. Rushing it would just leave you with buzzwords, not understanding. So here's the key rule for this video. Relaxed pacing, human language. No racing through slides, no walls of symbols. We're going to talk, imagine, and build this up like we're sitting at a table with a pen, a notebook, and maybe a cup of tea. Imagine we're building a house together. First, we pour the foundation. That's everyday gravity. Why does a hammer and a feather fall at the same rate in a vacuum? Why do you weigh a tiny bit less at the equator than at the poles? Why does it feel like the floor is pulling you up, even though we say gravity pulls you down? We'll make those ideas so solid you can feel them. Then we put up the walls. That's orbits. Why doesn't the moon crash into Earth? Why is the International Space Station in constant free fall and yet not falling down? Let me give you the clearest possible example. You fire a cannonball faster and faster until, instead of landing, it keeps missing the ground and goes around the planet. That's an orbit. Once that picture clicks, planets, moons, and satellites all start to make sense. Next, we add the upstairs floor, Einstein's new idea of space-time. Before we can understand black holes or warped time, we have to understand that gravity is not just a pull, but a bending of the stage. Everything moves on. We'll use simple mental experiments and the bedsheet and ball image so you can see, in your mind, how mass reshapes the paths of everything around it. Finally, the roof. Extreme gravity. Black holes, event horizons, spaghettification, and those tiny gravitational waves from colliding black holes that make detectors on Earth twitch by less than the width of a proton. Here's something that will make you smile. By the time we get there, those wild ideas will feel like natural extensions of the simple stuff we started with. Here's our learning contract. If you stay with the step-by-step explanations, do the little imagination exercises and pause when you need to, by the end you'll be able to explain gravity from your drop phone to 2 black holes merging to a friend in plain language. So get comfortable. Grab a drink, maybe a snack. Mentally commit to this as a story we're going to travel through, not a checklist of facts. because in the next section, we're going to start pouring that foundation, one falling object at a time. Now that we've agreed to treat this as a story, not a checklist, let's lay down the single sentence that secretly runs through the whole story. Gravity is the pull that every bit of matter has on every other bit of matter. All the time, no exceptions. I want you to let that land for a moment. Not just Earth pulling you down, not just the sun holding the planets. Every grain of sand, every drop of water, every brick in the building you're in and your body, your phone, the chair beneath you, all of them are quietly pulling on each other right now. You don't feel most of those tiny pulls, but they're there. Here's something that will make you smile. Your body is pulling on the earth just as much as the earth is pulling on you. They're a pair. The only reason you move and the earth barely twitches is that the earth has so much more mass, so it's harder to budge. Think about that for a second. You are, in a tiny way, tugging the planet. Let me give you the clearest possible example. Imagine you sitting in a chair. Your body pulls on the chair. The chair pulls on you. The chair and the floor pull on each other. The building pulls on the street. The street pulls on the rest of the city. Zoom out and the earth pulls on the moon, and the moon pulls right back on the earth, raising tides in the oceans. We live inside this web of mutual pulling. So what decides how strong that pull is? Two simple things. First, how much stuff there is, the mass. Second, how far apart the objects are. Here's the key rule. More mass means a stronger pull. Being closer means a stronger pull. Being far away means a weaker pull. That's it. Big and close? Strong gravity. Small and distant? Barely any. Imagine two people standing next to each other. They pull on each other, but so weakly you'll never notice. Put a mountain next to you. More mass, stronger pull. Stand on Earth. Now the pull is strong enough that if you drop your phone, you absolutely notice. Swap Earth for a black hole with the same mass squeezed into a tiny region, and that pull near the surface becomes so intense that even light cannot escape. Before we can understand warped space-time, event horizons, and why time itself slows near a black hole, we have to understand this one simple idea so well it feels boring. Gravity is universal pulling, stronger with more mass, stronger when closer. We're going to circle back to that same sentence again and again, from falling apples to colliding black holes, until it's second nature. So let's bring all of that big universal pulling right down to where you are right now. Not out with distant stars, not even with the whole earth. With you, your body, and whatever you're sitting or standing on at this exact moment. I want you to actually notice it. Feel the places where your body meets the chair, or the couch, or the floor. That gentle pressure under your legs or your back. The way your feet press into your shoes, and your shoes press into the ground. That squeeze, that push, that contact. That's what you usually call your weight. Here's the key rule. Your weight is not just how heavy you are. It's how strongly Earth's gravity is pulling on your mass in this particular place. Your mass is how much stuff you're made of, how much you there is. If you went to the moon, your mass wouldn't change at all. You wouldn't suddenly be made of less you. But the pull of gravity there is weaker, so your weight would drop to about 1/6. Same you, different pull, different weight. Think about that for a second. Let me give you the clearest possible example. Imagine you're sitting in a chair. Earth is pulling you down, constantly, but you're not sinking through the floor like a ghost. Why? Because the chair is pushing up on you. The atoms in the chair are packed together and they resist being squeezed. So as gravity pulls you down, the chair pushes back up with exactly the same force. Down pull, up push, perfectly balanced. That balance is why you feel heavy on the chair. Your body is slightly squished where it meets the seat. Your muscles are quietly working. Your skeleton is under load. You feel the push from below, not the invisible pull from Earth. Here's something that will make you smile. In everyday life, you never actually feel gravity directly. You only feel things pushing back against gravity for you. Now imagine something dramatic. The floor, the chair, everything solid under you just vanishes. Not gravity, just the support. In that instant, there's nothing left to push up on you. Earth's pull is still there, just as strong as before, but now there's no resistance. You start to fall. And the strange thing is, as you fall, that feeling of weight, that pressure, disappears. Your stomach might flutter, but your feet no longer press on anything. Your back isn't squashed into a seat. You feel weightless, even though gravity is still pulling on every bit of your mass. Before we can understand astronauts floating in a spaceship that's still deep inside Earth's gravity, or what happens near a black hole where falling never really stops, we have to get comfortable with this idea. Weight can vanish while gravity remains. In the next part, we're going to push that feeling of falling to its absolute limit and see why it might hold the secret to what space-time really is. So now that you've felt what it's like for weight to disappear while gravity keeps working in the background, we need to zoom out and ask a very simple question. What decides how strong that invisible pull actually is? I want you to hold on to one picture for the rest of this video because it's going to guide us all the way to black holes. Here's the key rule. Gravity cares about two things more than anything else. How much mass something has and how far away it is from you. That's it. More mass means a stronger pull. More distance means a weaker pull. Everything else is just detail layered on top of those two golden rules. Imagine you're standing in a field holding a tiny pebble in one hand and looking up at a mountain in the distance. The pebble is close. The mountain is far. Which one pulls on you more? The mountain wins easily because it has so much more mass. Think about that for a second. Even far away, a huge pile of rock beats a small stone right next to your skin. Let me give you the clearest possible example from everyday life. You're walking past a parked car on the street, and far across the city there's a skyscraper. The car is close. The skyscraper is far. The car's gravity is tugging on you, and so is the skyscraper's. But both of those pulls are absolutely crushed by something else. Earth itself. The planet under your feet has so much mass that its pull overwhelms the tiny arguments between the car and the skyscraper. Here's something that will make you smile. Technically, your body is pulling on the car too. Your mass tugs on everything around you. The chair you're sitting on, your phone, even the moon. But Earth is so absurdly massive compared to you that its gravity wins by a landslide. We're going to put numbers on that later, and you'll see just how hilariously outmatched you are. Now, there's a second part to our rule. Gravity gets weaker very quickly as you move away from something. Double the distance and the pull doesn't just gently fade. It drops off hard. That's why the sun, even though it's over 300,000 times more massive than Earth, doesn't rip you off the ground. You're much closer to Earth, so Earth's gravity on you is stronger than the sun's. Compare Earth, the moon, and the sun. The moon is smaller than Earth, so its pull is weaker overall. But when a spacecraft flies close by, the moon can grab it into orbit because distance suddenly favors the moon. Shift the distances, and the balance of power shifts too. Before we can understand what happens when mass is crammed into a tiny region, or why getting close to a black hole changes everything, we have to be fluent in this picture. More mass and closer distance equals stronger pull. In the next part, we'll finally start putting real numbers to that feeling and see how they shape orbits, falling, and eventually the edge of a black hole. We've talked about how more mass and less distance means a stronger pull. Now I want you to feel that rule in your own hand. Wherever you are, pause for a moment. Look around and pick up something small. A pen, a key, maybe your phone if you trust yourself not to drop it too hard. Hold it a little above a table or your desk. Not too high. Just enough that you can watch what happens. Ready? Let it go. Watch that tiny fall. It starts from rest. For a split second, it's just hanging there in mid-air. And then, as soon as your fingers release, it begins to move. Faster and faster and faster. Until, tap, it hits the table and comes to a stop. That speeding up, that smooth rush downward, is gravity turning stillness into motion. Imagine we could replay that same drop in ultra-slow motion. Frame by frame, the object would be a little lower, moving a little quicker, covering a bit more distance each slice of time. That change in speed is what physicists call acceleration. You don't need the symbol or the number yet. Here's the key rule. Near Earth's surface, gravity gives every freely falling object the same acceleration, no matter what it's made of. Think about that for a second. Your pen, a hammer, a gold bar, if air resistance didn't get in the way, they'd all fall together. The only reason a feather seems different is the air pushing back on it. Now, why is your pen accelerating at all? Because Earth is pulling on it. And Earth has a lot of mass, roughly 6,000 billion kilograms. That number is so big our brains basically give up. Compared to that, the object in your hand is nothing. It's like comparing a single grain of sand to an entire planet of rock. But here's something that will make you smile. The pen is also pulling on Earth, with the same force. That's Newton's deep insight. The pull your pen feels toward Earth is matched by an equal pull that Earth feels toward your pen. So why don't you see Earth leap up to meet it? Because Earth's mass is so enormous that the acceleration it gets from that tiny force is unbelievably small. The pen falls clearly. Earth moves too, but by such a microscopic amount that no human eye will ever notice. Technically, every time you drop a pen, you are making the entire planet move a little bit toward that pen. You are constantly, quietly, rearranging the universe, one tiny fall at a time. We're going to take this same simple drop, and in the next part, start putting numbers to it. How fast it speeds up, how weight and mass are different, and how all of that prepares us for places where gravity becomes so strong that even light cannot escape. So we've talked about how everything is always quietly falling, including you and the Earth itself. But there's a question hiding inside that idea that almost everyone asks at some point. If gravity is a pull, shouldn't heavier things fall faster than lighter ones? I want you to picture this. You're holding a bowling ball in one hand and a marble in the other. Same height, same starting point. Your everyday experience whispers, "Come on, the bowling ball has way more mass. It has to slam into the ground first." That feels right, doesn't it? Think about that for a second, because your intuition is about to get challenged in a pretty dramatic way. Let me give you the clearest possible example. Imagine you're standing on the moon next to an astronaut. In one hand, the astronaut holds a hammer. In the other, a feather. No air, no wind, no atmosphere at all. Just vacuum and gravity. They stretch out their arms, open their fingers, and let both objects go at the exact same moment. Here's the part that almost makes your brain do a double take. The feather and the hammer fall together. Side by side, they hit the lunar dust at the same time. No cheating, no slow motion trick. Real feather, real hammer, real moon. If you've never seen that clip, here's something that will make you smile. It looks like the universe is deliberately trying to mess with your expectations. So what's going on? Here's the key rule. When you take air out of the way, gravity gives the same acceleration to everything, no matter the mass. A tiny marble, a huge bowling ball, a feather, a hammer, even you. If they start from rest and fall freely, they all speed up at the same rate in that same gravitational field. On Earth, it doesn't look that way because our thick blanket of air is constantly pushing back. The feather isn't falling slowly because gravity likes it less. It's falling slowly because the air is shoving upward on all that fluffy surface. The bowling ball slices through the air. The feather gets tangled in it. Before we can understand black holes, we have to understand this much simpler trick. If you could somehow suck all the air out of a tall tower and drop a bowling ball and a marble together, they would fall side by side, keeping pace all the way down, and smack the floor at the same instant. Different masses, same fall. Now, why should the universe arrange things so that every bit of mass, from a grain of sand to a planet, shares the same free fall acceleration? That strange equality is not just a cute party trick of gravity. It is one of the big clues that led Einstein to a completely new picture of what gravity really is. And in the next part, we're going to follow that clue right up to the edge of a black hole. So let's take that clue and bring it right back to you, right now. Wherever you are sitting, standing, maybe lying on a couch, I want you to notice something that sounds impossible at first. In a very real sense, you are falling right now. Not in the dramatic roller coaster way, not with wind in your hair and your stomach jumping. But gravity is trying to pull your body along a natural path, and that natural path is free fall. Think about that for a second. If the ground, the chair, the building, everything solid under you vanished in an instant, what would happen? You wouldn't hang there politely, waiting for instructions. You'd immediately start to accelerate downward. Near Earth's surface, that acceleration is about 9.8 meters per second squared. Let me give you the clearest possible example. In the first second, you'd pick up about 10 meters per second of speed. After 2 seconds, about 20. After 3, about 30. Faster and faster the whole time, with gravity giving you that same steady push. That is your natural motion in Earth's gravity field. So why aren't you currently blasting through the floor like a cartoon character? Because the floor is fighting back. Right now, the ground is pushing up on you with exactly the same force your weight is trying to push down. Your body is constantly pressing into the floor, and the floor is constantly pressing back, preventing you from following that free fall path. Here's the pattern interrupt. We usually say, gravity is pulling me down. But you can flip the picture. Instead of thinking, gravity is pushing me into the floor, imagine, the floor is constantly pushing me up. It's holding you up against what gravity wants you to do, which is to fall. You feel that as pressure in your feet, or in the chair under you. That feeling of weight, that's not gravity itself. That's the floor refusing to let you fall. Here's something that will make you smile. Astronauts on the International Space Station are not floating because gravity turned off. They're only a few hundred kilometers above your head, and gravity up there is still about 90% as strong as it is for you. They float because they and their spaceship are in continuous free fall, always falling toward Earth and always missing. Before we can understand why orbits work and later why a black hole is so extreme, we have to understand this idea. Free fall is the most natural thing you can do in a gravity field. We're going to use that idea to explain why weightless really means nothing is pushing up on you anymore, and how simply falling can bend not just your path in space, but your experience of time itself. So if free fall is the most natural thing you can do in a gravity field, why do you feel heavy right now just sitting there? Why does the floor feel so solid under your feet instead of you floating like an astronaut? To answer that, we have to untangle two words people mix up all the time: weight and mass. I want you to imagine you have a magical label on every atom in your body that just says stuff. All the protons, neutrons, electrons that make you you. That total amount of stuff is your mass. It doesn't care where you are. Earth, moon, floating between the stars, standing dangerously close to a black hole's event horizon in your imagination. Same mass. Same amount of you. Your weight is different. Your weight is how hard gravity is pulling on that mass in a particular place. Think about that for a second. Same you, same amount of stuff, but the pull can change from world to world. Here's the key rule. Mass is what you bring. Weight is what gravity does to it. Let me give you the clearest possible example. Imagine you step on a bathroom scale on Earth. It might say 70 kilograms or 150 pounds. What it's really measuring is how hard the ground has to push up on you to keep you from falling, because Earth's gravity is pulling you down with a certain strength. That strength is set by Earth's gravity, this familiar downward acceleration we call g. Now we fly you to the moon. Same body, same clothes, same slightly suspicious scale. The moon is smaller and less massive than Earth, so its gravity is only about 1/6 as strong. Here's something that will make you smile. You step on the scale and suddenly it reads 1/6 of your Earth weight. You didn't diet on the way there, your mass is exactly the same, but the moon's weaker pull gives you a smaller weight. I want you to imagine walking outside in your spacesuit, wearing the same heavy backpack you use on hikes back on Earth. On Earth, that pack digs into your shoulders. You feel every step. On the moon, with 1/6 the weight, you can bounce, you leap higher, you land more gently. The backpack is still full of the same stuff, the same mass, but gravity isn't yanking it down as hard, so you feel light and springy. Now bring it back to your body, right where you are. The heaviness you feel in your legs, the pressure in the chair, the number on your scale. That's just Earth's gravity acting on your mass. If we could teleport you to Mars or to a giant super-Earth, your weight would change dramatically, but the collection of atoms that is you would not. In a moment, we're going to take this idea one step further and ask, what happens to your weight, and even your sense of up and down as gravity gets so strong that space-time itself starts to twist? So now we've separated your weight from your mass. You're the same collection of atoms wherever you go, but the pull of gravity can make you feel heavier or lighter. Let's push this one step further and do something strange. I want you to imagine what it would be like for that feeling of weight to vanish completely. Picture yourself in a totally ordinary place. An elevator. Nothing sci-fi yet. You're standing there, maybe holding your phone, feeling the floor firmly under your feet. That quiet pressure from below is so familiar, you almost never notice it. The floor is pushing up on you just hard enough to keep you from accelerating downward under Earth's gravity. Now, let me give you the clearest possible example of what gravity really feels like. The elevator starts to go up. You feel a little heavier for a moment as the floor presses more strongly on your feet. Then it slows to a stop, and you feel a tiny bit lighter. All of that is the floor changing how hard it pushes on you, not gravity changing. Think about that for a second. The pull from Earth barely changed at all, but your feeling of weight did. Here's where things get dramatic. Imagine that suddenly, with a horrible metallic snap, the elevator cable breaks. The car, you, your phone, your keys, the air inside, everything begins to fall together, pulled downward by gravity at exactly the same rate. In that instant, something magical happens. Inside the elevator, you feel weightless. The floor is no longer holding you up, so it stops pushing on your feet. If you let go of your phone, it doesn't crash to the floor. It floats right next to you. You could push gently off one wall and drift in the middle of the car like an astronaut. Here's something that will make you smile. In that brief, terrifying moment, your falling elevator has turned into a tiny space station. But notice the crucial thing. Gravity did not turn off. The pull of Earth is still there, dragging everything downward together. What disappeared was the support force, the push of the floor on you. Here's the key rule. The feeling of weight comes from being pushed on, not from gravity itself. Remove the push and you feel weightless, even while you're in full, honest, free fall. Before we can understand a black hole, we have to understand this simple elevator. Einstein realized that a freely falling elevator is locally indistinguishable from drifting in deep space, far from any mass. That single idea became one of his most important clues, leading him to a wild conclusion. Maybe gravity isn't really a force at all, but something deeper, something geometric. In the next step, we're going to follow him there and ask, what if falling is just the straightest possible path through a warped space-time? So now we're ready for a bigger view. Up to this point, we've stayed very local. Your body in a chair, a pen in your hand, the floor pushing up on you while gravity pulls everything down. We felt gravity in our muscles. We've watched it in those simple falling experiments. Drop a pen, it accelerates toward the floor. Drop your keys, same story. Different object, same pull, same steady acceleration. Think about that for a second. From your point of view, gravity has been this very down-to-earth thing. Literally. But the universe is not just your room. I want you to mentally step away from wherever you are right now. Stand up in your imagination. Walk through the ceiling. Keep going. Past the roof, past the clouds, past the thinning air, until the blue fades and you're looking back at Earth from space. You see a glowing marble. White clouds, blue oceans, brown continents slowly turning. Around it, against a deep black background, there's the moon. A pale, cratered ball, circling, circling, circling. Here's the question that should bug you. If gravity is always a pull that brings things together, why doesn't the moon just fall straight into the earth, the way your pen falls straight to the ground? It's clearly being pulled. It clearly wants to fall. So why is it still up there calmly looping around us after billions of years? Here's the key rule. There isn't one kind of gravity for dropped objects and a different, special orbit gravity for moons and satellites. The same gravity that makes your phone hit the floor is the gravity that keeps the moon on its path. Same Earth, same mass, same pull, just playing out on a much bigger stage. Let me give you the clearest possible example. Imagine you're on a very tall mountain with a cannon. You fire a ball gently sideways. It goes forward a bit and hits the ground. Fire it faster, it goes farther before hitting. Fire it faster still, and the ground starts to curve away beneath it as Earth bends around. If you could give it just the right sideways speed, it would keep falling toward Earth. But the ground would keep curving away at exactly the same rate. It would fall and never land. Here's something that will make you smile. That's basically what the moon is doing. It is constantly falling toward Earth because of gravity, but it's also constantly moving sideways fast enough that it keeps missing. So before we can understand black holes and extreme space-time, we're going to lock in this gentler idea. Falling around something instead of straight toward it. So let's zoom in from the moon for a moment and come back to something you can actually throw with your own hands. I want you to imagine you're standing in an open field with a ball. You hold it out at shoulder height and throw it straight sideways. Not up, not down, just level with the ground. What happens? It moves forward and it falls. Forward and down at the same time. If you could trace its path with a glowing line, you'd see a graceful curve, arcing through the air until it finally meets the ground. Gravity is pulling it toward Earth the whole time, but its sideways motion keeps it from dropping straight down like a rock. Now, let me give you the clearest possible example of how orbits really work. You throw the ball a little harder. It goes farther before it hits. You throw it harder again, farther still. Each time the same thing is happening. The ball is always falling, but while it falls, the ground under it is curving away, because Earth is round. Think about that for a second. The surface isn't flat and endless. It bends away beneath the ball. Here's the key rule. The faster the ball's sideways speed, the farther it travels before the ground catches up to its fall. If you could somehow throw it incredibly fast, much, much faster than any human arm, it would fall toward Earth, but the Earth would curve away beneath it at exactly the same rate. The ball would keep missing the ground. It would circle all the way around and come back to you, still falling, still missing. That never-ending missing is what we call an orbit. It's not that gravity turned off. It's that gravity is constantly pulling inward while motion is constantly carrying the object sideways. We're going to keep coming back to that balance because it's the same basic dance that planets, moons, and even stars perform. To make this feeling even clearer, imagine a ball on a string, and you're swinging it in a circle over your head. The ball wants to fly off in a straight line, but the string keeps pulling it inward toward your hand. In this little story, the string is gravity, Your hand is like the massive object in the middle. The ball's motion tries to escape. The pull keeps redirecting it over and over into a circular path. Here's something that will make you smile. The moon is basically a ball on an invisible string. It's a thrown ball going so fast sideways that it keeps missing Earth, forever falling but never landing. And in a moment, we'll push this gentle idea of falling around something to its absolute limit, into the territory where space-time itself starts to twist. Now let's zoom in on that ball on an invisible string and really feel what it's doing. I want you to imagine you're floating far above the Earth, far beyond the clouds, beyond the satellites, out where the blue fades to deep black. Hanging there in front of you is the moon. The moon looks close in the night sky, but it's not. It's about 384,000 kilometers away. That's such a big gap that even light, the fastest thing in the universe, needs just over 1 second to cross it. Think about that for a second. A beam from a flashlight on Earth would take longer than a heartbeat to reach the moon. Now, let me give you the clearest possible example of orbital motion using it. The moon is constantly being pulled inward by Earth's gravity. The Earth has mass, the moon has mass, and gravity never takes a break. At that distance, the pull is weaker than what you feel on the ground, but it's always there, tugging the moon toward us. So why doesn't it just crash? Because the moon isn't sitting still. It's also sliding sideways at about 1 kilometer every second. Picture that. Every single second, it moves roughly 1 kilometer along its path, while gravity bends that path inward. Sideways motion, inward pull, over and over. Here's the key rule. Orbit is just falling with enough sideways speed that you keep missing. The moon is in free fall, exactly like your pen was when you let go of it. The difference is space. There's so much room for it to fall around the Earth instead of straight into it. Same gravity, same idea, just stretched out to a huge, looping path. Imagine freezing time for an instant and turning off that sideways motion. The moon would have no choice but to start dropping inward, curving more and more steeply toward Earth. It wouldn't smack into us in one go. It would spiral, lose height, and eventually crash. Same pull, less sideways escape. Now imagine the opposite pattern interrupt. Keep the sideways speed, but magically turn gravity off. No pull at all. In that moment, the moon would stop curving and fly straight off into space along a tangent line, leaving Earth behind like a missed exit on a highway. Here's something that will make you smile. The simple pen, drop on your desk, and the grand dance of the Earth and moon obey the exact same rule. Gravity causes acceleration. We're going to take that rule and push it even harder next, into a place where the pull becomes so strong and space-time bends so much that even light itself can't keep orbiting and escape. Now, let's zoom out one more time. We're going to leave the Earth-Moon pair behind and look at the bigger stage they're performing on. I want you to imagine you're floating far above the solar system, looking down. In the center, blazing and bright, is the sun. Around it, the Earth traces out a nearly perfect circle, taking 1 year to complete a lap. It looks calm, predictable. But underneath that calm picture, the exact same drama of falling and missing is playing out again. Here's the key rule. Gravity is a pull between anything that has mass, and the more mass you have, the stronger your pull. The sun has an enormous amount of mass. Let me give you the clearest possible example of just how enormous. you would need about 330,000 Earths to match the sun's mass. Think about that for a second. Every ocean, every mountain, every city on Earth, multiplied hundreds of thousands of times, still only equals one sun. Because of that huge mass, the sun's gravity dominates the solar system. Its pull controls the paths of the planets, the comets, even tiny dust grains drifting between worlds. You, sitting on Earth, are actually part of a gigantic gravitational relationship with this star, whether you feel it or not. Just like the moon around Earth, our planet is in constant free fall. This time, it's free fall toward the sun. If gravity were suddenly turned off, Earth wouldn't gently drift away. It would shoot off in a straight line through space, like a car suddenly losing its steering on a curve. Instead, the sun's pull bends that straight path into a wide, graceful orbit. Here's something that will make you smile. Earth is not lazily strolling around the sun. It's racing. Right now, you're moving sideways at about 30 kilometers every second in your orbit. In the time it takes you to say gravity, you've already traveled dozens of kilometers along Earth's path. That sideways speed is exactly what keeps our planet perpetually missing the sun as it falls. So the pattern repeats. A satellite around Earth, the moon around Earth, the Earth around the sun, they're all the same story. Gravity pulls inward, motion carries sideways, and the result is an endless fall that curves into a loop. Change the masses, change the distances, change the speeds, and you get different shapes and sizes of orbits, but not a different idea. Before we can understand a black hole, we have to understand this simple picture of gravity as a pulling force shaping orbits. But here's the twist waiting for us. There's a deeper, stranger way to see gravity, not as a pull at all, but as the bending of space and time themselves. And near the most extreme objects in the universe, that new picture doesn't just help. It becomes the only one that works. So if gravity is this invisible pulling force shaping orbits, why do astronauts look like they've escaped it? They float, their hair drifts, tools just hang in the air. It really looks like space is a place where gravity has been turned off. But it hasn't. Not even close. I want you to imagine you're on the International Space Station looking down at Earth. You're only about 400 kilometers above the surface, not some enormous distance out in the galaxy. Here's the key rule. At that height, Earth's gravity is still about 90% as strong as it is where you're sitting right now. Think about that for a second. 90%. If gravity disappeared up there, the station wouldn't orbit. It would just drift away. So why does everything feel so different? Why do astronauts float when gravity is still pulling almost as hard as it pulls on you? To see it, we're going to connect this to the orbit picture you already have in your mind. The space station is like a miniature moon. It's constantly falling toward Earth because of gravity, but it's also constantly moving sideways, fast enough that it keeps missing. It doesn't fall down. It falls around. Now let me give you the clearest possible example. I want you to remember our falling elevator. You, the elevator, and everything in it all accelerate downward together. Because you and the floor are falling at the same rate, the floor stops pushing up on your feet. Inside that elevator, you feel weightless, even though gravity is absolutely still there, pulling on you the whole time. Here's something that will make you smile. The space station is basically the world's most expensive, never-ending falling elevator. The astronauts, the station, the experiments, Even that floating blob of orange juice you've seen in videos, they're all in continuous free fall around Earth. Gravity is pulling on every bit of them together, so nothing needs to press on anything else to hold it up. No push, no pressure, no weight. This is the real reason astronauts float. Not because there's no gravity, but because gravity is the only thing acting on them. Pattern interrupt time. Don't think of the space station as being outside gravity. Think of it as being inside pure gravity, with no solid ground to get in the way and push back. Once you see weightlessness as continuous free fall, a lot of strange things about space start to make sense. And in a moment, we're going to take this idea one step further and ask a deeper question. If gravity can make you feel weightless, what is it actually doing to space and time themselves? Now, to really see what gravity is doing, I want you to meet the person who first turned all these falling apples and orbiting moons into a single, sharp idea. Isaac Newton. Imagine him watching the moon glide across the sky and asking a very simple question. Is the same gravity that pulls an apple down also pulling the moon toward the Earth? Here's the key rule Newton discovered. Every object with mass pulls on every other object with mass. Your body, the chair, the Earth, the sun, everything is pulling on everything else all the time. The pull gets stronger if the masses are bigger, and it fades as things get farther apart. Think about that for a second. You are literally pulling on the sun right now, just so weakly that no one will ever notice. Let me give you the clearest possible example. Take the Earth and the sun. The sun is huge, so its gravity is strong. The Earth is constantly falling toward the sun under that pull, just like the International Space Station is constantly falling toward the Earth. But the Earth is also moving sideways fast enough that, instead of crashing in, it keeps missing. The result is an orbit, a graceful, endless fall around the sun. Here's something that will make you smile. Using just Newton's gravity, people could predict where planets would be in the sky years, even centuries, in advance. They could figure out that Neptune had to exist before anyone had actually seen it, simply because Uranus was wobbling a little wrong. That tiny wobble was the pull of another unseen planet. And it didn't stop there. The same Newtonian gravity lets us design spacecraft paths, slingshotting probes around planets to save fuel. It explains why you get 2 high tides a day, because the moon's pull stretches the oceans, and even why you weigh a tiny bit less at the equator than at the poles. One simple idea, and suddenly the whole solar system becomes a predictable machine. Before we can understand black holes, we have to understand this. For almost everything you ever do, Newton's picture works brilliantly. Engineers still use it to build bridges, plan flights, and send satellites into orbit. If you drop your phone, if you jump, if a planet circles a star, Newton's gravity will tell you what happens next with incredible accuracy. But now, we're going to start pushing gravity to its limits. What if something is moving close to the speed of light? What if the mass is so huge and packed into such a tiny region that the pull becomes extreme? Near places like black holes, or when we need to measure time itself with ridiculous precision, Newton's beautiful picture starts to crack. In the next step, Einstein walks in and quietly changes what we mean by gravity at all. So let's zoom in on those cracks, because this is where gravity starts to feel strange. Newton's picture works so well that it's easy to forget to ask, wait, how is this supposed to happen exactly? When you push it to the edge, the old story of a simple pulling force begins to wobble. I want you to imagine the sun suddenly shrinking or moving. In Newton's universe, the pull of gravity changes everywhere at the exact same instant. The Earth would know right away and adjust its orbit immediately. But there's a problem. From other parts of physics, we have this rock-solid rule that nothing, no signal, no influence, can travel faster than light. Think about that for a second. Instant gravity changes would be faster than light, by an infinite amount. That clash is like a big red warning light. Something in the picture is incomplete. Let me give you the clearest possible example of another crack. Mercury. Mercury is the tiny, fast planet closest to the Sun, racing around in a tight, hot orbit. If you use Newton's gravity to calculate that orbit, you get an answer that is almost perfect. Almost. Over time, the point where Mercury comes closest to the Sun slowly shifts, like the orbit is drawing a rosette instead of a simple ellipse. Newton can explain most of that shift from the pull of other planets, but not all of it. There's a leftover bit that refuses to go away. For decades, that tiny mismatch sat there quietly whispering, "Your theory isn't the full story." Now, let's talk about light itself. Light has no mass in the everyday sense. So in Newton's world, why should gravity pull on it at all? And yet, when we look near very massive objects, we see light bending, stars appearing in the wrong place, galaxies smeared into arcs. How do you bend something that, according to the old rules, shouldn't even feel gravity? Newton's gravity doesn't really tell you. It just sort of shrugs. Here's the key rule. Before we can understand black holes, we have to understand why this older map of gravity starts to distort on the biggest scales. Newton's theory is like a beautifully accurate street map of your city. For getting from your house to the grocery store, it's perfect. But if you try to stretch that same flat map over the whole round Earth, lines that were straight start to curve, distances stop adding up, and you get lost. The map wasn't wrong. It just wasn't made for the whole planet. We're going to do the same thing with gravity. We're going to pull back from the local, everyday view and look at the universe-size version. And here's something that will make you smile. The person who fixed Mercury's orbit, gave gravity a speed limit, and showed how light can bend was not fixing Newton with duct tape. Albert Einstein threw out the idea of gravity as a simple pull and replaced it with something far stranger. In the next section, we step into his space-time, and that's where black holes finally start to make sense. So let's walk into Einstein's world together. I want you to imagine him not as a wild-haired wizard on a poster, but as a person staring at a very simple question and refusing to let it go. What if gravity isn't really a force at all? What if it's telling us something about the shape of space and time themselves? Before we can understand black holes, we have to understand that question. Think back to the elevator and free fall ideas. If you're floating inside a falling elevator, you feel weightless, even though Earth's gravity is still very much there. If you're drifting in orbit, like an astronaut on the space station, you feel free, even though Earth is still pulling on you. Think about that for a second. The places where gravity is strongest can feel like the places where gravity disappears. Einstein obsessed over that feeling. He noticed that when you're in free fall, you don't feel a pull anymore. You just feel normal, calm, as if you're gliding along the path you were always meant to take. He took that feeling seriously and made a bold move. He said that free-falling motion is actually the most natural motion there is. Here's the key rule in Einstein's picture. If nothing is pushing or pulling on you, you don't curve your own path. You follow the straightest possible line through space-time. But here's the twist. In his view, space-time itself can be curved. So what looks to you like a curved path around Earth or around a black hole is, from space-time's point of view, just you stubbornly going straight in a landscape that's bent. Let me give you the clearest possible example. Imagine rolling a marble across a perfectly flat floor. It goes straight. Now imagine a rubber sheet stretched tight with a heavy bowling ball in the middle. The sheet dips. If you roll the marble near the dip, its path bends around the bowling ball, even though you never touch the marble. No invisible string. No mysterious hand. The surface's shape guided the motion. Einstein's big idea is that mass and energy are like that bowling ball. They tell space-time how to curve, and curved space-time tells matter and light how to move. Gravity stops being an invisible pulling force and becomes the way objects respond to the geometry they live in. Now, I know curved space-time can sound abstract, so we're going to keep it friendly. Stretched sheets, rolling balls, elevators, and simple stories instead of heavy math. In the next section, we'll push that sheet analogy to the extreme and see what happens when you cram so much mass into one region that space-time doesn't just dip, it caves in. That's when a black hole is born. So let's make this curved space-time idea something you can actually see in your mind. I want you to imagine you're standing next to a giant trampoline or a huge rubber sheet stretched tight in a frame. Perfectly smooth, perfectly flat, no dips, no wrinkles. That flat sheet is our picture of empty, uncurved space-time. Walk around it in your imagination for a moment. If you gently roll a marble across this flat sheet, it just goes straight. No surprise. Straight line, steady speed, nothing to get in its way. In Einstein's language, that marble is following the straightest possible path in space-time. On a flat sheet, straightest possible path just means straight. Now, let me give you the clearest possible example of what mass does. Take a heavy bowling ball and place it right in the center of the trampoline. The rubber sags. The sheet dips down around the ball, making a kind of bowl-shaped valley. You didn't tug on the marble. You didn't add a mysterious new force. You just changed the shape of the surface. Here's something that will make you smile if you've ever played with a real trampoline. Roll that same marble again, but this time send it near the heavy ball. What happens? Its path bends inward. It might swing around the bowling ball in a loop or spiral in and crash, depending on how fast you give it a push. Think about that for a second. Nothing is pulling on the marble with a string. It's just following the easiest path available on a curved surface. Here's the key rule. Before we can understand a black hole, we have to understand that this is how Einstein wants you to see gravity. Mass doesn't reach out with invisible hands and pull on everything. Instead, mass curves the sheet of space-time, and everything with mass, or even light itself, moves along the straightest possible paths in that curved geometry. Now, for the pattern interrupt. In this picture, gravity is not something sitting on top of space like an extra ingredient you sprinkle in. Gravity is the shape of space and time themselves. Change the mass, you change the shape. Change the shape, you change how things move. You're not being pulled down by a force as much as you're being guided along a path in curved space-time. In the next section, we're going to take that same rubber sheet and keep adding mass, more and more squeezing it into a smaller region until the dip becomes so extreme that the surface doesn't just sag, it caves in. That's when the gentle valley of gravity turns into the bottomless pit of a black hole. So far, we've been treating that rubber sheet of space-time like it's just a surface you could walk across, a place where marbles roll and valleys bend. But space-time has a secret you absolutely cannot ignore. It isn't just space. Time is woven into it. I want you to imagine that every point on that rubber sheet doesn't just say, "here in space." It also carries a little built-in clock, a tiny ticking heart that tells you how fast time is flowing there. When mass bends space-time, it doesn't only curve the paths that objects follow. It also stretches and squeezes those little clocks. Here's the key rule. The deeper you are in a gravitational well, the slower your clock runs compared to clocks higher up. Strong gravity doesn't just pull on you, it drags on your time. Think about that for a second. Gravity is quietly changing how fast now moves for you. Let me give you the clearest possible example. If you put a super precise clock on the floor and the same kind of clock on a high shelf, the one on the floor, just a bit deeper in Earth's gravity, ticks more slowly. Not by much, but measurably. Take it further. A clock at sea level runs a tiny bit slower than a clock on top of a mountain. And a clock on a plane or a satellite, higher up in weaker gravity, runs faster still. Here's something that will make you smile. Your phone's GPS only works because engineers take this seriously. The satellites above you experience weaker gravity than you do on the ground, so their clocks naturally tick a little faster. If we ignored that and didn't correct for the difference, your location would drift by kilometers each day. Your map app would slowly lose its mind. Now imagine two identical twins. One spends their whole life living in a cozy house at sea level. The other moves to a cabin high in the mountains. Same planet, same gravity source, just slightly different depths in Earth's gravitational well. Over a lifetime, the mountain twins' clock runs a tiny bit faster. At the end, they would actually be older by a fraction of a second. Not enough to notice at a birthday party, but real enough that our best instruments can see it. Before we can understand what happens near a black hole, we have to understand this gentle version here on Earth. Because near truly extreme gravity, this effect stops being gentle. As you get closer to the edge of a black hole, time for you would slow down so much that from far away, it almost seems to freeze. In the next section, we're going to push this idea to the limit and watch what happens to time itself at the brink of a bottomless pit. So now we know that gravity can slow time and bend paths, but there's a puzzle sitting right under your feet. If space-time around Earth is curved, why does your living room floor look perfectly straight? Why does your kitchen clock tick along like nothing weird is happening at all? I want you to look around, wherever you are. The walls are straight, the ground feels solid and flat. Time feels steady. You don't wake up in the morning thinking, "Wow, I'm walking on a curved space-time surface today." You just walk. Think about that for a second. If gravity is really this bending of space-time, why don't you feel the bend? Here's the key rule. Curvature can be real and still be hard to notice locally. Let me give you the clearest possible example. Imagine a tiny ant walking across a gigantic, smooth beach ball. The ball is obviously curved if you see the whole thing. But for the ant, whose world is just a few centimeters wide, its little patch is basically flat. Every step feels straight, even though, globally, it's walking on a sphere. You and I are like those ants. Earth has a lot of mass. Its gravity is strong enough to hold oceans in place and keep our atmosphere wrapped around us. But on the scale of space-time curvature, Earth is actually pretty gentle. Over the few meters of your room or the few seconds between glances at your watch, the bending of space-time is tiny. So your path feels straight, your time feels smooth, and everyday life feels Euclidean and calm. Here's something that will make you smile. Your body is constantly following the straightest possible path through curved space-time, and the floor is what keeps rudely interrupting you. If we suddenly removed Earth, you wouldn't feel a new pull. You'd feel nothing at all as you drifted. That nothing is you gliding along the natural curve of space-time, pure free fall. So how do we actually notice the curvature? We notice its effects. Falling objects all accelerate the same way because they're all trying to follow those natural space-time paths. Planets orbit the sun not because they're being yanked by an invisible rope, but because space-time itself is curved around the sun, guiding their motion. And with very precise clocks, we can measure that time on GPS satellites high above Earth ticks, slightly faster than time on the ground. All of that is Earth's gentle version. To really see space-time curvature with your mind, we're going to have to leave this comfortable, almost flat neighborhood and head somewhere far more extreme. In the next part, imagine diving toward a place where gravity becomes so intense that not even light can escape. And watch what that does to space, time, and you. So let's leave that almost flat neighborhood around Earth and start turning the gravity knob up. I want you to imagine we're flying away from our planet, but we're going to carry Earth's gravity with us as our baseline, like a ruler we can compare everything else to. On Earth, gravity feels solid and familiar. It keeps your feet on the ground, shapes the oceans into rolling waves, and makes a dropped phone head straight for the floor. It's strong enough to hold an atmosphere, carve rivers, and keep the moon in its path, but gentle enough that you can still jump, run, and, on a good day, maybe do a cartwheel. Think about that for a second. This invisible pull is powerful, but you and I can push against it. Now we dial things up and visit Jupiter. Same basic idea of gravity, just more of it. Jupiter is a giant ball of gas with more than 300 times Earth's mass. Stand on a solid platform at the level we call its surface, and you'd feel more than twice Earth's pull. Your body would feel heavy, your steps slow and labored, like you were wearing a backpack full of rocks. A jump that sends you a foot off the ground here might barely lift you a few inches there. But Jupiter is still the gentle league. To really feel extreme gravity, we need something not just more massive, but much, much denser. Let me give you the clearest possible example. Before we can understand a black hole, we have to understand its little cousin, a neutron star. Imagine taking the sun's mass and squeezing much of it into a sphere only about as wide as a city. 20 kilometers across instead of more than 1 million. Same kind of mass, unimaginably smaller space. Here's the key rule. When you cram a lot of mass into a tiny volume, gravity at the surface skyrockets. On a neutron star, surface gravity can be millions of times stronger than Earth's. If you somehow hovered a meter above the surface and stepped off, you wouldn't gently fall. You'd slam down at a huge fraction of the speed of light in less than a second. No time to scream, no second try. Standing there, if that were even possible, your body would be crushed flat and stretched at the same time by the insane difference in pull between your head and your feet. So strong, so extreme, so unforgiving that normal matter, atoms, even the idea of solid ground starts to break down. Here's something that will make you smile. Compared to that, Earth suddenly feels like a cosmic pillow. And yet, even a neutron star hasn't crossed the final line. Light can still escape, if just barely. If we squeeze even more mass into an even smaller space, the curvature of space-time becomes so intense that escape would require something faster than light. Since that's impossible, not even light gets out. That's our next destination. The moment gravity stops just being a pull and becomes a one-way door. So what is this one-way door, really? What is a black hole in the simplest possible language, the kind that you can keep in your head and actually use? I want you to imagine you're standing on Earth, looking up at the sky, and you launch a rocket straight up. If it's too slow, gravity pulls it back down. If it's fast enough, it escapes and never comes back. That special fast enough is called the escape speed. Think about that for a second. It's not about turning gravity off. It's about having enough speed to outrun its pull. For Earth, that escape speed is about 11 kilometers per second. For the Sun, it's much higher. For a neutron star, it's incredibly high. Now keep cranking up the density, squeeze more and more mass into a smaller and smaller ball. The escape speed climbs. At some point, if you squeeze enough, the escape speed doesn't just get big. It passes the ultimate speed limit of the universe, the speed of light. Here's the key rule. Nothing can move faster than light. Not rockets, not particles, not information. So if you create a region where the escape speed is higher than light speed, then nothing that crosses into that region can ever get out again. That, in plain language, is a black hole. A region of space where gravity is so strong that nothing, not even light, can escape once it gets too close. But here's something that will make you smile. Black holes are not cosmic vacuum cleaners roaming around, sucking up everything in sight. If you magically replaced the Sun with a black hole of the same mass, Earth would keep orbiting almost exactly as it does now. No sudden drain, no dramatic slurping sound. The gravity far away would feel the same. It's the near part that gets wild. In Einstein's picture, what's really happening is that space-time itself is curved so extremely that once you cross a certain boundary, all possible paths you could take bend inward. It's like being in a valley so steep that every step, every jump, every desperate rocket burn still leads down. Not because something is grabbing you like a hand, but because there simply is no path that leads back out. That invisible boundary has a name, the event horizon. Before we can understand the inside, we have to understand that horizon. It's the point of no return, the surface beyond which events can't send any signal to the outside universe. In the next parts, we're going to slow down and unpack all of this. How such a thing can form from real stars, what the event horizon really means, and how time and space themselves start to behave strangely near a black hole. So let's actually watch one of these things form. Not in a computer simulation, but in your mind. I want you to imagine a massive star, many times heavier than our sun, living out its long, bright life. Inside, it's been a constant battle. Gravity is always trying to pull all that mass inward, squeezing everything tighter. Fusion in the core pushes back, flooding the star with energy and pressure. For millions of years, those two effects balance almost perfectly. The star feels calm on the outside because there's a silent war on the inside. But that balance doesn't last forever. As the star ages, it fuses heavier and heavier elements. Hydrogen, then helium, then carbon, climbing the periodic ladder until it reaches iron in the core. And here's the key rule. Fusing iron doesn't give you extra energy out. It actually costs you energy. So the core runs out of useful fuel. The outward pressure from fusion fades. Think about that for a second. Gravity has been patiently waiting, and suddenly its opponent just weakens. Now gravity wins. The core begins to collapse. Not slowly, but in a catastrophic inward plunge. The same mass is forced into a smaller and smaller volume, so the density and the inward pull skyrocket. In some stars, that collapse slams to a halt when electrons get packed as tightly as they can. The result is a white dwarf, Earth-sized but with the mass of a star. In heavier stars, even that isn't enough, and protons and electrons get crushed together into neutrons. Then you get a neutron star, only about the size of a city, but with more mass than the Sun. Let me give you the clearest possible example of how extreme that is. A teaspoon of neutron star material would weigh as much as a mountain. Here's something that will make you smile. If you ever feel like you're carrying a lot, just remember, the universe can do much worse. But for the most massive stars, even a neutron star can't hold itself up. The collapse keeps going. As the radius shrinks, the surface gravity increases, and so does the escape speed, the speed you'd need to launch yourself away and never fall back. On Earth, that's about 11 kilometers per second. For a neutron star, it's a big fraction of the speed of light. Keep shrinking the same mass further, and something wild happens. At a certain radius, the escape speed would have to be faster than light itself. And since nothing can beat light, that means nothing can get out. At that moment, an event horizon forms, a one-way surface where light can fall in but never return. The star's core is now hidden from the universe, sealed behind that dark boundary. What's really inside that region, and what does gravity do there when it has no competition at all? That's where our understanding starts to shake and where we're going next. So now we have this dark boundary, this event horizon, wrapped around the collapsed star. But what actually is that boundary? Is there a wall there? A surface you could bump into with a very unfortunate thunk? Not at all. I want you to imagine something much stranger and much cleaner. The event horizon is not a solid shell of stuff. It's an invisible boundary in space-time itself, defined only by what paths light and matter are allowed to take. No bricks, no glass, just geometry. Here's the key rule. Outside the event horizon, there are still paths that lead outward. If you fire a rocket in the right direction with enough speed, you can escape. If a beam of light is aimed just so, it can curve around the black hole and head back out to the wider universe. Think about that for a second. Even right next to a black hole, out still exists. But as you move closer, those paths get rarer and more twisted. Gravity is bending space-time so hard that most directions you could travel start to tilt inward. It's like standing on a steep hillside. You can still climb up, but more and more of the ways you could step would send you sliding down. Let me give you the clearest possible example. Imagine a wide, calm river flowing toward a gigantic waterfall. Far upstream, you can splash around, swim in circles, even lazily drift, and still make it back to shore. The current is gentle. There are plenty of ways to paddle away. Now move closer to the drop. The water speeds up. You can still escape, but you have to swim harder and in a more careful direction. Finally, you reach a place where the current is so strong that no matter how fast you swim, you're going over the edge. That invisible line in the water where escape becomes impossible is the river's event horizon. Cross it and all paths lead down. A black hole's event horizon works the same way, but with space-time instead of water. Outside it, some paths for light still bend outward. At the horizon itself, all possible light paths are tilted so steeply inward that none of them lead out anymore. Light is trapped, and so is everything else. Here's something that will make you smile. From your point of view, nothing special has to happen right there. You just keep falling. Before we can understand what comes next, we have to understand one more twist. You learned earlier that orbits are just objects falling around in curved space-time. The event horizon is the place where space-time is curved so extremely that falling around is no longer an option. Inside that boundary, every possible future is a fall inward. So what does that fall feel like? And what happens to you as you get closer to the center? That's where things get stretched, strange, and very, very interesting. So, let's zoom in on that fall. You're not just dropping into darkness. You're heading into one of the strangest experiences gravity can offer, with a name that sounds almost silly. Spaghettification. Physicists really do call it that. Spaghettification. Here's something that will make you smile. One of the most extreme death by gravity scenarios in the universe is named after pasta. But behind the playful name is a very serious idea about how gravity behaves when it gets unbelievably strong. Before we can understand spaghettification, we have to understand something called tidal forces. I want you to imagine you're floating out in space far from any black hole. Gravity from distant stars and galaxies is pulling on you, but it feels the same on your head, your feet, your left side, your right side. Everything is so far away that the pull is almost perfectly even. Now start falling toward a black hole, feet first. As you get closer, gravity changes fast with distance. Your feet are a little closer than your head, so they feel a slightly stronger pull downward. Think about that for a second. One part of your body is being yanked harder than another part. That difference is the tidal force. Let me give you the clearest possible example. Imagine your body as a soft, stretchy cylinder. The black hole pulls more strongly on the bottom than the top, so it stretches you along your length. At the same time, gravity is pulling inward from the sides, squeezing you thinner and thinner, stretched in one direction, squashed in the others. That's spaghettification. You're literally being drawn out into a long, thin strand, like a piece of spaghetti. This isn't some brand new rule of the cosmos. It's the same tidal effect that raises ocean tides on Earth because the moon pulls a bit harder on the near side than the far side. Near a black hole, though, the change in gravity with distance is so steep, so intense, so rapid that your body becomes its own little tide chart. Here's the key rule. The smaller the black hole, the more brutal the tidal forces near the event horizon. For a tiny, stellar mass black hole, the difference in gravity between your head and your feet becomes extreme well before you cross the horizon. You wouldn't get a chance to admire the view. You'd be stretched and torn apart first. But for a supermassive black hole, like the one at the center of our galaxy, it's surprisingly different. The event horizon is so large that the change in gravity over the length of your body can be gentle. You could drift right through that point of no return and, at least at first, not feel anything special at all. That's the pattern interrupt. Spaghettification sounds like a wild, exotic effect, but it's really just gravity's most familiar rule, stronger when you're closer, turned up to an extreme. Next, we're going to see how that same rule starts to twist not just your body, but time itself. So let's turn that dial one more notch. We've stretched you into cosmic spaghetti. But now, I want you to actually take the fall. Not in a cartoon way, not in a sci-fi movie way, in a real, physics as we understand it way. Imagine this. You're in a sleek little space pod, dropped toward a black hole. Far away, at a safe distance, your friend hangs back in another ship with a powerful telescope pointed right at you. You wave, you check your watch, you feel the gentle hum of the engines. And then, the engines cut out. From this moment on, gravity does all the work. Here's the strange part. As you fall, you don't feel the pull as a force yanking you down. You feel weightless. Just like astronauts orbiting Earth, you and your pod are in free fall, following the natural curve of space-time. If you let go of a pen, it floats next to you. Your stomach doesn't stay behind. To you, the fall feels calm, almost boring. Let me give you the clearest possible example of how weird this is. There's a sharp, terrifying boundary around the black hole called the event horizon. Cross it, and not even light can escape. You might expect alarms blaring, dials spiking, some dramatic shudder as you pass this point of no return. But from your own perspective, nothing special happens right there. Your watch ticks normally. Your heartbeat feels steady. In a perfectly smooth fall, you cross the horizon in a finite amount of time, and you don't notice the exact moment. Now, switch seats. Think about that for a second. What does your friend see through the telescope? From their safe distance, your story looks completely different. As you approach the horizon, your friend sees your clock ticking slower and slower. Your waves of light climb out of the black hole's gravity well, losing energy on the way, so the signals arriving at their ship get redder and weaker. Your voice on the radio stretches out lower and slower, like someone leaning on the universe's slow-motion button. Here's something that will make you smile in a slightly nervous way. From your friend's viewpoint, you never quite make it. You seem to freeze right at the edge of the event horizon, moving slower and slower, fading away as your light gets too dim and too red to detect. For them, you are forever stuck on the border. So who's right? You, who falls straight through, or your friend, who never sees you cross? Here's the key rule. Near a black hole, gravity doesn't just bend space, it bends time. Time itself runs slower, deeper in the gravity well than it does far away. We're going to dig into that more soon, but for now, hold on to this. Both stories are real, depending on where you are. And inside the horizon, where every path the future can take dives inward, all roads lead to a mysterious center we call the singularity, a place where our current physics starts to whisper, stutter, and then go silent. Now I want you to imagine something strange. We've been bravely following gravity's rules all the way down into a black hole, watching time stretch and paths bend. But as we aim for that mysterious center, something uncomfortable happens. Our best maps of physics start to tear. Physicists call that center the singularity. In simple terms, it's the place where, if you just trust the math of general relativity, the density of matter and the bending of space-time shoot up to infinity. Infinite density, infinite curvature. It sounds dramatic, almost like a sci-fi exaggeration, but it's really a warning label. Think about that for a second. Here's the key rule. Whenever a theory spits out infinity for something that should be a real, physical quantity, it's not telling you that the universe literally did that. It's telling you, I've been pushed past where I can be trusted. So when Einstein's gravity says right here everything becomes infinitely squeezed, it's not describing a real, infinitely tiny point. It's waving a little white flag. Let me give you the clearest possible example. Before we can understand the singularity, we have to understand what our theories are good at. General relativity is amazing at describing big things, planets, stars, galaxies, the way mass tells space-time how to curve and that curve tells everything how to move. Quantum mechanics is amazing at describing tiny things, atoms, particles, the jittery, probabilistic world on the smallest scales. But a black hole's center is both incredibly massive and squeezed into an incredibly small region. That's exactly where we need both theories at once. And right now, they don't play nicely together. So when you hear singularity, don't picture a magical, infinitely small dot with truly infinite density. Instead, picture the place where our math breaks. It's like you've zoomed in so far on the universe that the pixels of our theories are showing. We think what we actually need there is a new, unified description. A quantum theory of gravity that merges Einstein's smooth space-time with quantum mechanics' grainy, jittery behavior. Here's something that will make you smile. The singularity is a bit like the edge of an old sailor's map, where the cartographer ran out of information and just wrote, "Here be dragons." That phrase tells you more about the limits of the map maker than about the actual ocean. In the same way, singularity tells us more about the limits of our current physics than about what's really happening to the matter that fell in. And that's okay. It's genuinely okay not to have a clear picture of what's inside the very center. What we do understand extremely well is everything outside that edge of the map. The event horizon, the way gravity pulls on nearby stars, how matter heats up and shines in X-rays as it spirals in, how black holes merge and send out ripples of space-time we can measure on Earth. So for the rest of this journey, I want you to keep this in mind. The singularity is our "here be dragons" zone. We'll respect it, acknowledge it, and then focus on what we can actually test and measure. Because right outside that mystery, black holes are already doing something even stranger to reality itself. They're messing with information and time in ways that might rewrite how we understand the universe. So if black holes aren't just magic mystery points, what are they doing out there? Now we need to clear up one of the biggest myths in all of space science. Black holes do not roam around the universe sucking up everything like giant cosmic vacuum cleaners. I want you to imagine the classic cartoon version for a second. A black hole drifts by, starts slurping up stars, planets, maybe the hero's spaceship like water going down a drain. It feels dramatic. It feels scary. But it's wrong in a really important way. Here's the key rule. Outside a black hole's event horizon, its gravity works just like the gravity of any other object with the same mass. Not almost like it, exactly like it. If you're far away, you don't feel that it's a black hole. You just feel mass pulling on you. Let me give you the clearest possible example. Imagine, very gently, that we could take the sun, and compress it down into a black hole without changing its mass at all. Same mass, same place, just incredibly compact. What would happen to Earth? Think about that for a second. Your first guess might be that we'd get sucked in. But Earth's orbit would keep going almost exactly as it does now. We'd freeze in the dark, yes, but we would not spiral down some cosmic bathtub drain. Why? Because Earth is already in orbit. It's moving sideways fast enough that it keeps missing the sun, or, in this case, the sun-turned black hole. Gravity is still a pull, space-time is still curved, and Earth is still just following that curve. So when does a black hole feel different? Only when you get very close to it, near the event horizon. That's where the curvature of space-time becomes extreme, where the difference in gravity between your head and your feet can stretch you, and where no path leads back out once you cross the point of no return. Far away, normal, up close, absolutely wild. Here's something that will make you smile. A black hole is less like a hungry monster with suction and more like a very dense, very compact bowling ball sitting on that imaginary rubber sheet of space-time. It doesn't reach out with a vacuum hose. Objects still have to come close, or lose orbital energy, or bump into gas and dust to actually fall in. Pattern interrupt. The sucking image isn't just a little off, it actually hides the more interesting truth. Black holes aren't cosmic mouths trying to eat everything. They're regions of extremely warped geometry, places where the rules of space and time themselves get bent to the breaking point. And once you see them that way, you're ready for something even stranger. How that warped geometry starts to play games with information and with time itself. If black holes are regions where the rules of space and time get bent to the breaking point, that raises a very simple question. How do we know they're really out there? You can't exactly point a telescope at extremely warped geometry and snap a selfie. So how do you detect something that, by definition, doesn't let light escape? I want you to imagine standing in a dark field at night. You can't see the wind itself, but you can see trees swaying, grass bending, clouds racing across the sky. The wind is invisible, but its effects are not. Black holes are like that. Inside the event horizon, no light gets out, so the black hole itself is truly dark. But the universe around it, that's where the story lights up. Here's the key rule. We don't look for the black hole. We look for what it does to everything nearby. A massive, invisible object will still pull on stars with its gravity. If you see a star whipping around an empty-looking point in space on a tight, fast orbit, you can work backward and calculate how much mass must be hiding there. Think about that for a second. You're weighing something you can't see, just from how it makes other things move. Let me give you the clearest possible example. At the center of our galaxy, there's a radio source called Sagittarius A star. Astronomers have spent decades tracking individual stars near it, watching them trace tiny loops on the sky. Some of those stars complete an orbit in just about 16 years, racing at thousands of kilometers per second around nothing we can see. When you do the math, all those orbits point to about 4 million times the mass of the sun squeezed into a region smaller than our solar system. There's no known way to pack that much mass into that little space without making a supermassive black hole. Now add gas to the picture. When gas spirals toward a black hole, it doesn't fall straight in. It forms a swirling disk, rubs against itself, heats up, and glows. Sometimes it gets so hot it shines in X-rays. So, oddly, Some of the brightest objects in the universe are actually powered by the darkest ones. Here's something that will make you smile. A black hole can light up an entire galaxy core. And then there's the famous portrait. The Event Horizon Telescope didn't see the black hole itself. It saw a glowing ring of hot gas with a dark patch in the middle. That dark patch is the black hole's shadow, the region where light paths are bent so strongly that they plunge inward and never come back. So we can't see black holes directly, but we can see their fingerprints everywhere, in orbits, in glowing gas, in cosmic shadows. And there's one more way, completely different from all of this. Instead of seeing black holes, we're going to learn how to hear them through tiny ripples in space-time called gravitational waves. Instead of seeing black holes, we're going to listen to them, not with ears, but with the fabric of the universe itself vibrating ever so slightly. I want you to imagine space-time as a kind of invisible, stretchy medium that fills everything. When something with mass just sits there, it simply dents this medium. But when masses move and accelerate, especially when they're really massive, they don't just sit in their dents. They stir the medium. They send out ripples. Those ripples are what we call gravitational waves. Here's the key rule. Any accelerating mass can make gravitational waves, but almost all of them are unbelievably tiny. You waving your arms? Technically, yes, you're making waves in space-time, but they're so weak that even if we turn the entire Earth into a detector, we'd never notice. To feel them, you need something extreme. You need a black hole or two. Now, what are these waves actually doing? They're not sound waves in air. They're not light waves in space. They are tiny stretches and squeezes of space itself, racing outward at the speed of light. As a gravitational wave passes through you, the distance between the atoms in your body changes by a minuscule amount, then goes back to normal. You don't feel it. Your chair doesn't feel it. But space felt it. Think about that for a second. The universe has a way to send out news about violent events, not by throwing particles at you, but by rhythmically changing what distance even means. Let me give you the clearest possible example. Picture two black holes, each maybe dozens of times the mass of the sun, orbiting each other. At first, they're far apart, circling slowly. As they orbit, they radiate gravitational waves, and those waves carry away energy. When they lose energy, they spiral closer. Closer means faster. Faster means stronger waves. The whole system winds up like a cosmic siren. Now I want you to zoom in on the final moments. The black holes are whipping around many times per second in a region smaller than a city. The waves they send out grow in pitch and strength until merger. One bigger, quivering black hole settles down, and the waves fade. If you convert that motion into sound, what reaches Earth is a brief, rising chirp that lasts a fraction of a second. Here's something that will make you smile. In 2015, the LIGO experiment actually heard that chirp. Two giant L-shaped detectors, each with arms 4 kilometers long, used lasers to measure changes in length smaller than a fraction of a proton's width as a wave passed. From over 1 billion light-years away, colliding black holes tugged on the size of an instrument on Earth. Gravitational waves gave us a brand new sense, a new way to feel the universe. But they also whisper a deeper puzzle. We can hear space-time ringing, yet we still don't understand how gravity, this smooth bending of space-time, fits with the jittery quantum world of particles. To go further, we'll have to walk right into that tension And that's where things get very strange. Now, I want you to imagine something a little uncomfortable. We just listened to space-time itself ring like a cosmic bell. And yet, at the deepest level, our two best instruction manuals for the universe don't actually agree with each other. Think about that for a second. On one side, we have general relativity. This is Einstein's masterpiece, the theory you've been getting to know in this video. It treats gravity as smooth bending of space-time caused by mass and energy. It explains planets orbiting, GPS satellites ticking, black holes forming, even those tiny gravitational waves washing through the Earth. When the universe is big and the masses are large, relativity is our gold standard. On the other side, we have quantum mechanics. That's the theory of atoms and particles, of electrons jumping between energy levels, of light coming in tiny packets called photons. Quantum theory is jittery, probabilistic, and built on a very different kind of math. It describes how everything behaves when you zoom in so far that individual particles and their strange rules start to matter. Here's the key rule. Both theories work unbelievably well in their own domains. If you want to predict how a black hole bends light, use relativity. If you want to predict how an electron orbits a nucleus, use quantum mechanics. Let me give you the clearest possible example of how good they are. Without quantum corrections, your phone's electronics wouldn't work. Without relativity corrections, its GPS would slowly drift kilometers off target. But here's something that will make you smile in a slightly nervous way. When we try to turn both manuals on at once, they start arguing. Inside a black hole, mass is squeezed into an unimaginably tiny region. Near the Big Bang, the entire universe was packed into something even denser. Those are places where gravity is incredibly strong, and things are incredibly small at the same time. Relativity says space-time is a smooth fabric. Quantum mechanics says, at tiny scales, reality flickers and foams. Which one wins? Right now, we don't have a complete quantum theory of gravity, a single framework that tells us how space-time itself behaves when it has to follow quantum rules. We have ideas, string theory, loop quantum gravity, and others, but nothing that everyone agrees is the final story. So it's like this. We're going to run the universe, and we've been given two instruction manuals. Both are beautifully written. Both have passed every test in their own ranges. But in overlapping situations like the heart of a black hole, they give conflicting instructions. Which manual do you trust when everything is on the line? Before we can understand what really happens at a singularity, or exactly how information behaves in and around a black hole, we have to understand that this clash isn't a failure of science. It's science doing its job. We know where our current ideas break. We know gravity extremely well in almost every situation you'll ever encounter. And the remaining mystery? That's the invitation. In the next part, we'll step even closer to that edge and see what these puzzles might be trying to tell us. So far, we've been walking right up to the edge of what we know about gravity. Now, I want you to take one more step with me because gravity is about to reveal something the universe is hiding. Not a tiny detail, a huge missing piece. Imagine you're looking at a spiral galaxy from above, like a glowing cosmic pinwheel. You see the bright center, the sweeping arms, the stars scattered like city lights at night. If you add up all that visible stuff, the stars, the gas, the dust, you can estimate how much mass it has. And from that mass, you can predict how fast the stars should orbit around the center. That's the easy part. But when astronomers actually measure those speeds, something strange happens. The stars far out in the galaxy, way in the dim outer regions, are moving too fast. They're whipping around almost as quickly as the inner stars, instead of slowing down. Think about that for a second. If only the visible matter were there, gravity's pull should get weaker with distance, and those outer stars should drift more lazily. Here's the key rule. If you spin something too fast and there isn't enough gravity holding it in, it flies apart. A galaxy with only the matter we can see should be tearing itself to pieces. But it isn't. It holds together beautifully. So either gravity stops working the way we think it does out there, or there's more mass than meets the eye. Let me give you the clearest possible example. Imagine you're orbiting that galaxy in a little spaceship, measuring how fast stars go at different distances. Every time you move outward, you expect the speeds to drop. They don't. It's as if the galaxy is embedded in a huge, invisible halo of extra mass, adding more and more gravity you can feel, but not see. We call that extra stuff dark matter. Not because it's spooky, but because it doesn't emit light, reflect light, or block light the way normal matter does. It just doesn't glow. It passes through telescopes like they're not even trying. But it still has mass, and mass means gravity. So the only way we know it's there is by the way it pulls on everything else. In that sense, dark matter is a lot like a black hole we can't see directly. Before we can understand what it is, we have to understand what it does. We watch how stars move, how galaxies within clusters tug on each other, how light from distant galaxies gets bent and stretched as it passes by. From those motions and distortions, we infer the hidden mass, shaping them. Here's something that will make you smile. Gravity has quietly turned into a detective tool. It's not just a thing we explain in textbooks. It's the very method we use to discover entire oceans of matter we can't see at all. And in the next part, we're going to push this even further and ask, if gravity can expose invisible mass, what else might it be trying to tell us about the deep structure of the universe? So if gravity can act like a cosmic detective, reading hidden mass in galaxies, what is it doing right under your feet, right now, on this very planet? I want you to imagine we zoom all the way back from clusters of galaxies and stop above Earth, just hanging in space, and we really look at our home. From far away, Earth looks like a perfect blue marble. Smooth, round, simple. But here's the key rule. Whenever something in physics looks too simple, look closer. As we drift in, you see it's not a perfect sphere at all. It's very slightly squashed at the top and bottom, and a little bit bulged around the middle. Think about that for a second. Our entire sense of down is built on a planet that's basically a gently squeezed ball. Why is it squashed? Rotation. As Earth spins, every bit of rock, ocean and you is trying to move in a straight line, but gravity keeps pulling everything inward. At the equator, that spin is fastest, so matter is flung outward just a tiny bit, making a bulge. Near the poles, the spin doesn't fling things outward as much, so the surface sits closer to Earth's center. Now, let me give you the clearest possible example of how this affects you. Imagine you're standing at the equator. Earth's gravity is pulling you toward the center, but because the planet is spinning, there's also a small outward centrifugal effect from your circular motion. It's not a real force in the same way gravity is. It's what you feel because you're constantly being turned in a circle instead of flying off in a straight line. Add those together, and the effective gravity you feel at the equator is slightly less than the raw pull of Earth's mass. Go stand at the pole, and things change. You're almost not moving in a circle at all, so that outward effect nearly disappears. You're closer to Earth's center, the pull of gravity is a bit stronger, and nothing is helping you cheat by pushing you outward. Here's something that will make you smile. That means you actually weigh more at the poles than at the equator. Same body, same mass, same breakfast, different number on the scale. We're talking less than 1%, but it's real. Your mass doesn't change, but your weight, the force you feel from gravity plus motion, does. So on one single planet with one single amount of mass, gravity, rotation, and motion all team up to decide how heavy you feel. Once you see that, you're ready for a wild idea. If spinning a planet can tweak your weight, what could spinning a spaceship do? In the next part, we're going to take these quiet little effects you've just understood and use them to design artificial gravity for space stations and sci-fi worlds, and see what would actually work in real life. So let's cash in that wild idea. If spinning Earth can gently change how heavy you feel, what happens if we build a ship whose whole purpose is to spin? Now we're not just living with gravity, we're trying to fake it. First, I want you to clear up one thing in your mind. We cannot just walk into a spaceship, flip a switch, and turn gravity on like a lamp. Real gravity comes from mass-bending space-time, and unless your ship secretly hides a black hole in the basement, you don't have enough mass to do that. But you do have something else: motion, acceleration. And your body is surprisingly easy to fool. Here's the key rule. You don't actually feel gravity itself. You feel whatever has to push on you to keep you from falling. Think about that for a second. On Earth, the ground pushes up on your feet. In orbit, astronauts float because both they and the ship are falling together, with nothing pushing on them. So if we can arrange for a floor to keep pushing on you in space, your brain will happily label that feeling as gravity. Imagine you're in a huge rotating ring like those classic sci-fi space stations. As the ring spins, you move in a circle. Your body wants to go straight, but the floor keeps turning you, constantly nudging you inward. To you, it feels like you're being pressed outward against the floor. Your feet sink in slightly, your muscles work to hold you upright. You can drop a ball and watch it fall down to the outer wall. It feels astonishingly like standing on Earth. Let me give you the clearest possible example. Picture swinging a ball on a string above your head. The string is always pulling inward to keep the ball going in a circle. In orbit, that inward pull is gravity, keeping a satellite from flying off into space. In a spinning habitat, we flip the story. The structure provides the inward pull, and you feel the outward push against the wall as your artificial weight. But here's something that will make you smile and maybe win you a sci-fi argument with a friend. Most movies get the details wrong, spin too fast, and your inner ear rebels. You feel dizzy, nauseous, disoriented, because different parts of your body are curving at slightly different speeds. To make it comfortable, the station has to be big, with a large radius, so you don't need many spins per minute to mimic Earth's gravity. Large radius means huge structure, huge cost, huge engineering headaches. Now, for a pattern interrupt. Artificial gravity sounds like we're inventing a new kind of gravity field. We're not. We're going to see that it's really just clever choreography, using acceleration and circular motion to recreate the same pushes and pulls your body already associates with weight. In the next part, we'll push this idea to its limits and ask what happens when you bring real extreme gravity, black holes, back into the story. So instead of just talking about clever choreography, I want you to actually feel it. Not in a giant space station, but right where you are with things you already have at home. Because before we can understand the most extreme gravity near a black hole, we have to understand how it shows up in the simplest little experiments. First one, a drop test. Very simple, very powerful. Grab two objects that are roughly the same shape but clearly different in mass. Maybe a big metal spoon and a plastic spoon, or a full water bottle and an empty one. Hold them side by side at the same height. Now, really watch closely and let them go at exactly the same time. They hit the ground almost together, don't they? Think about that for a second. Gravity is pulling harder on the heavier object because it has more mass, but it also has more inertia, more reluctance to speed up. Those two effects cancel, and the acceleration ends up the same. That equal acceleration is the quiet rule behind everything from falling apples to orbiting planets. Now let's slow things down. Imagine you tie a small weight, like a key or a washer, to a string and make a simple pendulum. Hold it to one side and let it go. It swings back and forth, tracing out this calm, regular arc. Here's the key rule. Gravity is always pulling the weight toward the lowest point, acting like a restoring force that tries to bring it home. The higher you start it, the more energy you give it, but the basic rhythm stays wonderfully predictable for small swings. Let me give you the clearest possible example. If you time 10 swings in a row, then do it again, you'll get almost the same number. You've just built a tiny gravity-powered clock. Now we're going to get a bit more dramatic. Carefully. Take a sturdy cup that you can grip well, put a little water in it, and in a safe space, swing it in a vertical circle like a loop-the-loop. When you go fast enough, even at the top of the circle, the water stays in. Here's something that will make you smile. For a moment, the water doesn't feel gravity pulling it out of the cup. The inward acceleration of the circular motion is matching or beating gravity's pull downward, so the water is pressed into the bottom instead of falling out. It's the same basic trick we'll use to fake gravity in spinning habitats. You don't even need props, though. Your own body is a gravity detector. Pay attention the next time you're on a playground swing and you rush through the bottom of the arc. You feel heavy there, light at the top. Or when a car goes over a hill a little faster than you expected, and your stomach flutters for a moment. Or when an elevator starts and stops and your weight seems to change. In each case, gravity itself hasn't changed, but your acceleration has. So your effective gravity, the push or pull you actually feel, does. If you try any of these, I want you to notice not just what happens, but how it feels in your body. Then tell me, did your spoons land together? Did your pendulum keep time? Did your cup keep its water? Did your stomach do that little roller coaster flip? Share your results and your weirdest gravity sensations, because once you've played with gravity yourself, you're ready to follow it all the way to the edge of a black hole in the next part. So now, you've swung spoons, dropped cups, and felt your own stomach react to falling. Let's zoom out and stitch all of that into one simple story. One story that runs from your phone, right there in your hand, all the way to the edge of a black hole. Here's the key rule. Everything with mass pulls on everything else. Your phone pulls on Earth. Earth pulls on your phone. The sun pulls on Earth. And a black hole pulls on all of them. Think about that for a second. The same invisible tug is connecting every object you've ever dropped to the most extreme objects in the universe. Newton's picture was beautifully direct. Gravity is a force. You have two masses. There's a pull between them, and that pull gets weaker with distance. Let me give you the clearest possible example. You let go of your phone, Earth's mass pulls on it, and the phone accelerates downward at about 9.8 meters per second squared. Simple, predictable, and incredibly useful. But then Einstein comes along and says, imagine something deeper. Before we can understand black holes, we have to understand that gravity isn't just a pull, it's geometry. Mass and energy bend space-time, and objects simply follow the curves. Your phone isn't being yanked by an invisible hand. It's following the straightest possible path through a space-time that Earth has gently warped around itself. Now stretch that idea outward. The same curvature that guides your falling phone also guides the moon as it falls around Earth in its orbit. The International Space Station is not outside gravity, it's in constant free fall, forever missing the ground. Astronauts float not because gravity is gone, but because everything around them is falling together. Increase the mass. Squeeze it into a smaller and smaller region. The space-time dents get steeper. The paths bend more dramatically, and the escape velocity climbs. At some point, the curvature is so extreme that even light, moving as fast as anything can move, cannot climb back out. That's when we give it a special name. A black hole. Here's something that will make you smile. The same four ideas, mass, distance, motion, and curvature, explain your phone screen cracking, the tides, GPS satellites needing tiny time corrections, and two black holes colliding and sending out gravitational waves we can hear on Earth. One rulebook, wildly different scenes. I want you to notice how your feeling about gravity has changed. It started as down, as weight, as that annoying thing that makes you pick stuff up off the floor. Now, it's a layered story you can retell. A universal pull, a curved space-time, gentle near your feet, fierce near a black hole. And here's the real twist. Once you see gravity this way, standing up, walking across your room, and looking at the night sky, stop being separate experiences. They become one connected picture. In the next part, we're going to push this picture until it almost breaks and ask, if gravity ties everything together so neatly, why does it also lead us straight into some of the biggest mysteries in physics? Now that we've stretched that picture of gravity until it was almost ready to snap, let's pause and look at what you can actually do with it. I want you to imagine pressing pause on the universe for a second and checking in with your own brain. You haven't just watched a video. You've basically taken a mini course in how gravity really works. Here's the key rule for what comes next. Understanding isn't about memorizing symbols. It's about being able to tell the story. And you can tell a lot of it now. You can explain why objects fall in plain language, not because down is special, but because Earth's mass curves space-time, and the straightest path through that curve happens to intersect the floor. Think about that for a second. Dropping your phone is you watching space-time in action. You can explain why weight and mass feel different, even if we use those words loosely in everyday life. Mass is how much stuff there is in you. It doesn't change when you stand on the moon. Weight is how hard gravity has to pull the floor up into your feet to keep you from falling freely. Let me give you the clearest possible example. In deep space, your mass is the same, but you feel weightless because nothing is pushing back on you. You can also explain why astronauts float without saying, "There's no gravity up there," because now you know that's wrong. The International Space Station is still deep in Earth's gravity well. Astronauts float because they're in constant free fall, always falling around Earth instead of straight down. Same gravity, different motion, totally different feel. Orbits, you've got those too. A planet, a satellite, even a tiny rock is just following the curved space-time around a bigger mass. Give it the right sideways speed, and it keeps missing the ground, looping endlessly. You can walk a friend from a ball on a string, to the moon, to the path of the Earth around the sun, all with one simple picture. And black holes, the most intimidating part of the story, are no longer mysterious monsters. You can say, a black hole is what you get when so much mass is squeezed into so small a region that the space-time curve becomes a cliff. The event horizon is the line where even light's fastest possible dash still can't climb out. Here's something that will make you smile. You can now sit down at a kitchen table or on a bus and, without a single equation, take someone from "Why does my coffee fall?" all the way to "How can two black holes make ripples in space-time we can hear on Earth?" That's real, meaningful mental work. Your brain has been building new connections this whole time. So here's a gentle challenge. Today, explain just one piece of this story to someone else. Maybe why astronauts float, or what a black hole really is. As you say it out loud, you'll feel which parts you truly own. And in the next section, we're going to use that as a springboard to push into the strangest open questions gravity still hasn't answered. And now, I want you to bring your own brain into the experiment. You've been listening, imagining space-time as a kind of flexible stage, following apples and black holes and astronauts. Now I'd love to hear where gravity used to feel like a magic trick instead of something you could really understand. Think about that for a second. Was it the idea that you're actually falling toward Earth but the ground keeps getting in the way? Was it Einstein's claim that you're not being pulled down, you're being pushed up by the floor? Or maybe it was black holes, how something can be so dense with so much mass in such a small space that light itself can't escape. Tell me in the comments which part of gravity confused you the most before this video, and whether it feels clearer now. Here's something that will make you smile. Your confusion is not a bug, it's data. When you say, "Wait, I still don't get why a hammer and a feather fall together," you're pointing right at the edge where your picture of the world is updating. So share that. If you had an aha moment anywhere in this story, describe it. Someone else is going to read your words and suddenly feel their own click into place. Now let's make this physical. I want you to try at least one tiny home experiment and then report back. Maybe you drop a spoon and a book at the same time and notice they hit together. Maybe you rig a simple pendulum from a string and a key and see how it swings the same way over and over, tracing out gravity's steady pull. Maybe you spin a cup of water in a circle and notice how the water stays stuck in the cup, the way the moon stays in orbit by constantly falling around us. If you do any of that, tell me exactly what you tried and what you saw. If you feel brave, film a 10-second clip and describe the result in your comment. Let me give you the clearest possible example. I dropped a sock and a shoe from my balcony. They landed together. It felt weird that mass didn't matter. That one simple sentence is already you doing physics. Here are a few reflection questions to play with as you type. What surprised you most about gravity? Did Einstein's view of curved space-time change how you feel when you're just standing on the ground, realizing the planet is quietly bending the stage under your feet? When you look up at the stars tonight, does it feel different to know that their light has threaded its way through valleys and hills in space-time to reach your eyes? We're going to collect especially interesting or common questions from do black holes ever stop growing? To what actually happens at the event horizon? To how can gravity affect time? And I may build a whole follow-up Q&A video around them. So if there's a piece of this that still feels slippery, put it in the comments. The odds are thousands of other people are wondering the same thing. Here's the key rule beneath all of this. Curiosity is the real engine of science. Your questions and kitchen table experiments live on the same long road that runs from a falling apple to GPS satellites correcting for time dilation to LIGO, listening to colliding black holes. When you wonder out loud, you're joining that project. In the next section, we're going to take that shared curiosity and aim it at the biggest open puzzles, the places where gravity itself seems to whisper, I'm not done revealing my secrets yet. Now, I want you to do one last thing with me. Wherever you are, pause for a second and notice the simple, ordinary weight of your body. Your feet on the floor, your back against the chair. The way the ground feels so solid, so steady, so absolutely there. I want you to imagine pulling the camera back. First, you see the room around you. Then your building. Then your city. Keep going. The continent, the blue curve of Earth. Think about that for a second. You are sitting on the skin of a spinning planet, and that planet is quietly bending space-time underneath you. True stillness. The kind where you feel like you're not moving at all. But in reality, Earth is racing around the sun. The sun is orbiting the galaxy, and the galaxy itself is gliding through the universe. You're not being yanked by invisible strings. You're following the curves of a cosmic stage that your own mass helps to shape. Let me give you the clearest possible example. Picture the Earth's space-time dent, like a smooth, deep valley. The moon is a runner on that curved track, always falling inward, always moving sideways, tracing its endless loop around us. Farther out, the planets are doing the same dance around the sun. And tucked inside galaxies, black holes make the valley so steep, so extreme, so powerful that light itself has no path that leads back out. Here's the key rule, wrapped into one line. Gravity is the way mass and energy curve the stage of space-time, guiding how everything moves, from your own body in that chair to the most distant galaxy we can see. Now carry that with you. The next time an elevator starts and your stomach flutters, you'll know it's your path through space-time tilting for a moment. When you drop your phone, hopefully onto something soft, you'll feel the floor pushing up, keeping you from following your natural free fall. When you step outside at night and see the moon, or hear about gravitational waves and colliding black holes in the news, you'll be able to say, I actually understand the story behind that. And here's something that will make you smile. Every time you simply stand there doing nothing special, you are part of the same grand script that guides stars, galaxies, and those wild, invisible ripples in space-time. If this journey helped gravity finally click for you, if it made that invisible pull feel calmer, clearer, less mysterious, then please take a moment to like this video, subscribe to the channel, and share it with someone who's always been curious about black holes or why anything falls at all. Wherever you are, whatever you're doing, gravity is quietly at work, holding you to a world that's surfing through space-time. And now, when you feel that weight, you'll know the story behind it. Thanks for watching and for bringing your curiosity along for the ride.